Okay, great. So hello everyone. My name is Theo, and yeah, today we'll talk about the work from Feldman and Zernik about individual privacy accounting with Rényi filter. So um, this is the agenda for today. There's a lot of topics to go through. So yeah, let's jump straight into it. So the main topic of the paper is privacy loss composition, which is of course a fundamental question in privacy preserving data analysis. But informally, what we are trying to do is analyze the degradation of each individual's privacy as more analysis use their data. So a visual example for that would be if we have a data set and we try to run an algorithm M1, let's say, over them, we get an output. And now if we want to do that again, we have to feed that output into our new analysis. And then for the third instance, we need to feed both A1 and A2. So our goal in this scenario is to find a bound over the privacy loss of the final algorithm in terms of privacy losses of each individual algorithm. And this approach is great because it's very easy to design algorithms around it, because then you allow individuals to take part in multiple analysis. Um, However, if we are going to composition in epsilon dp, but it can be, to be honest, this is more of a general. Uh, oh, okay, I forgot to do that. So if we go about a composition theorem in dp, most of them would look something like that. We can have a mechanism m of j. If we say that mj is epsilon j dp for all j's between 1 and n, then their composition, the final algorithm, is a sum of a j epsilon j dp. So if we go back to the examples with the data sets, um, hmm, um, then we can see that we have some new parameters, epsilon 1, 2, and 3. I think there's a problem. Okay, anyway. We can we can see that the overall analysis would be sum of epsilon j dp. And the problem here, or rather an issue, is that as many composition theorems, we summarize each algorithm's effect on the privacy by only one parameter over the whole data set. And this parameter should, of course, describe the worst case effect due to the removal of the extreme point. So how would that look, for example, if we are thinking of a very simple scenario where we have a company and people that would like to have a mean of their salaries without um, telling each other their salary. In this scenario, we can see that people that have an average salary close to the mean don't really contribute that much to the final computation. So their exclusion is not that impactful as to say, of course, extreme point. So actually, considering just this worst case parameter, this worst case effect in our parameterization, what's happening is that we are consuming more privacy for the average data points, and that might be inefficient, or actually, yeah, that can be considered inefficient. So the solution the authors propose is individual privacy counting, where they have this fine-grained approach where they actually evaluate the effect of each individual in the data set for each mechanism mj. So and yeah, they call this individual privacy loss. And of course, this could allow for a tighter analysis of privacy composition. So if we go back to our example where we have these three algorithms with the same data set and one parameter for each instance, now we get actually one parameter for each individuals in each instance. So 15 parameters in this case. Yeah. So before continuing their analysis, we have to talk a little bit about Rényi individual privacy. So they use this to do their analysis, but that's not really a problem because it can be converted later to epsilon delta dp. And here is the definition for RDP. We see that a mechanism satisfies this, or rather satisfy alpha rho j RDP for each individual x, y, xi, if the parameters follow this property. Here, d of alpha is the Rényi difference, divergence, sorry, Rényi divergence parameterized by the order alpha. And if we have an example, if as an example, let's consider mj as a gradient query, their formula might look something like that. The sum of the over the gradient and a little bit of noise at the end. Then mj would satisfy this if the loss is realized by the gradient, not by the worst case bound. And this is how the final results for the parameter would look like. And what is very interesting here is that the final parameter is described by the norm of the gradient for each point, not the worst case. It's not the sensitivity over the whole data set or over the function. And this actually will solve the problem with consuming too much privacy for the average data points. But another problem is that now these parameters are sensitive. We cannot just output them however we like. We cannot publish them. We have to be careful how exactly we use them. Okay, now if we go back to the adaptive composition, because we need to compute the effect on a specific point on a specific analysis, then we have to do this adaptively, and for that we have to do adaptively. We have to solve this problem with adaptively chosen privacy parameters, which was already done by Ruth, Rogers, Ullman, and Vadhan for epsilon dp. And they use a privacy filter, which they define as a privacy filter, as a stopping rule that ensures our privacy budget is met. So if we go back to the visual example, we might have this function f of b, where b is our overall budget, and if the condition of continuity is met, of not continuity, if the filter doesn't hold, then we can actually get our output, and we can then do that for each different instantiation, adding the privacy parameters in each situation. Of course, maybe the filter will hold, and then we will have to stop the computation, and we can make sure, okay, now we've used as much as possible given our model. But of course, we can stop even before that. Okay, and now the main contribution of the paper was this new composition theorem for RDP that follows these adaptive parameters. So how does that look? Is that if we fix a budget and an alpha, then mj is alpha rho j RDP, where rho j is an arbitrary function, if the sum of rho j will be smaller than b. I mean, it holds almost surely. Then we say that the composition of all these algorithms is alpha b RDP. So this is actually a filter for RDP because, one, we have a stopping rule based on the sum of RDP parameters, and two, we get the final results using the RDP composition with adaptivity in privacy parameters, because rho j will be a function of all the other outputs.
Just a question before. Yeah. So does the filter hold when? What's the stopping condition exactly for the filter? Is it something predefined, or
it has to be something like the sum of rho j is bigger than the budget. So when we have the results of a computation, and we notice that the sum of our parameters is bigger than the budget we were allowed to use, then we can halt and be like, okay, we don't publish the results. We are only allowed to publish the results before that. But I will have a visual example that should clarify this.
Okay, thanks.
So now regarding the question, if we look at an example for privacy filtering, let's say we start with our whole data set and algorithm M1, and we compute the rho for each individuals, and we notice, okay, everybody is within the budget. That's fine. We can output the result. Now, let's say that for the second algorithms, we do the same computation for the raw parameters, and we notice that for the orange stickman, the sum of their parameters exceeds the budget. So we have to hold for him. What does that mean is that we can remove him from the data set and output the results using only the data from the individuals for which the filter didn't hold. Now, we can continue doing this, and maybe we can notice that multiple people hold, and of course, we can eliminate more people. It's not really a restriction to eliminate only one person. And of course, we can do that until maybe there's no more people left, and then we have um, no results, or we can also we can stop even before. However, the main point is that the overall output of how many computation we'll do in the end is guaranteed to be alpha b Rényi differential private. Now we will take a look at one of their experiments, which was private gradient descent with IDP, and they used a setting from this paper. But the overall idea is pretty simple: is that you clip the gradient and you add the noise. So here you can see we've initialized the parameters. Of course, it can be arbitrarily. And now after we compute the gradients, we clip them. But very interestingly, we only clip them if the norm is bigger than our range C. So usually in the settings from 2016, from this paper, we would clip every gradient, but using this approach, what happens is that there are gradients which norm is lower than the C. So what we are doing in the end is we are saving on the privacy budget, and this allows us to do more iteration of this algorithm. Now, in the end, we have the noise, and of course, we can take the gradient step. Yeah, and this here is the interesting part. Okay. Now, lastly, we will say a few words about IDP and PySift. So in PySift, we are building these pipelines for structured transparency, where we want to have both input and output privacy and a few other properties. And IDP has become the main tool for output privacy in this remote data science pipeline. However, we did face some challenges, and there are still problems that we haven't fully fixed and we are actively working on. The first one is scalability for nonlinear queries. If you have noticed in the beginning, we only discuss about linear queries. Over the presentation, we only discuss about linear queries, where computation is pretty easy, but for nonlinear queries, you still have to take the sensitivity of a function into account. The authors propose using the Lipschitz bound of the function, but this doesn't scale that well for a lot of parameters. We did implement an optimization algorithm to find the results for the biggest gradient given the input, but it only works for a few values. It doesn't scale to millions of rows and so on. So yeah, that's still a problem that you have to take into account, how exactly to solve nonlinear queries. Then the second one would be computing queries across multiple domain nodes. Domain nodes in PySift are different servers where people can upload their data and do computation. So computing across these servers with input privacy has been a bit problematic, because if you remember, I did specify that rows in themselves are not secure because they actually depend on individuals' data. So you can't really just send them around. You have to be very careful with that. So that is still a challenge. We did try to do SMPC with it, but we had some noise amplification. So yeah, that's still a problem that we can improve on. Then computing queries across multiple data sets with overlapping data subjects. The main point is that if we have individuals being part that have data that takes part in a function, from multiple different sources, then we have to find that, we have to keep that in mind when computing the parameters, because then we basically know like why would we do that if we would qualify the same data subject at different data subjects. We would lose a lot on the privacy budget. And this complicates a bit the design, because then you have to keep a registry, like we call it a registry, but you can call it whatever, of different data subjects, and you have to have this ability to dynamically identify the data subjects across multiple data sets. So yeah, that complicates a bit the design, but the benefits are there once things are working. And then the last problem is filtering for nonlinear queries. So again, in linear queries, it's very easy to implement IDP and especially filtering, because you just don't add them. It's very easy to dismiss them. However, when you have functions that you can take whatever form, you might have your data. A simple example would be to have your data as a denominator to a function, to a fraction, and if during filtering the result of the denominator would be 0, then you would have this error doing parameterization, which would be very impactful, because maybe you could get a non-zero value if you'd filter one more person, but it's pretty hard to figure that out. Yeah, that's a new level of complexity that you have to take into account, that in nonlinear queries, even though maybe you can find a way to easily compute Lipschitz bound, you still need a more advanced filtering mechanism to avoid NaN values uh, in the wild. So yeah, those are these are the main challenges we face. And on some of them we are still working. Okay, so lastly, here's a list of the most relevant updates that have been done by the community since the publication of the initial paper. The one that is most important to us would be the first one. That so these authors of the first paper, what they did is they did the same analysis, but they replaced RDP with GDP, and their claim is that this is even a better relaxation or a tighter analysis, because it allows you to run even more iteration for the same algorithm. However, some of the problems still arise, but a very great improvement that they did is that they found a way to improve the time of the computation time of the parameters using FFT. So yeah, if you're interested in that, it's a very interesting result. Here is some work on filters and odometers in RDP, of course, mostly in DP, but yeah, that's if you're interested in that, you can go with that. And then we have some other improvements in composition, and I think the authors claim that they have like the best results in composition, and demonstrably you can't really get any better than that. And lastly, we have private or publish per instance privacy, or PDP, and somehow they have a similar idea. They acknowledge, hey, parameterizing over the whole dataset may be inefficient. Maybe we lose a bit on the budget there. Let's try to avoid it. Let's try to do a per instance instead. And yeah, I think they also have a lot of different analysis. I think also for cumulative DP. I'm not sure. I imagine also for RDP. I don't quite remember. Yeah, and as a conclusion, yeah, we looked at the tighter privacy accounting method that tracks the personalized privacy laws for every individual. The authors also showed in their paper that this approach is no more conservative than the worst case approaches. It actually, in the real world, it will be better, because you'll have a lot of different average data points. It's also pretty simple to implement for linear queries. We have talked a bit about nonlinear queries and the main challenges that arise from them. And another thing that I didn't really um, expand on is that this can be implemented in the local model if you are interested into that, as opposed to having a global model of privacy. Yeah, that's something that's useful. Okay, so yeah, if you have any questions, now would be a great time. Oh, um, what are the main advantages of using Rényi filter for individual privacy accounting compared to other privacy preserving techniques? Um, so others, you're referring to um, other DP methods or just other non-DP privacy preserving techniques? I will have to say that um, I don't really know a lot of others output privacy methods, but comparing Rényi filtering with let's say epsilon DP, the main advantage is the number of iteration. Yeah, okay. So at that time, I think they have one of the um, they achieve one of the best accuracy because they can get a very good, a very big number of iteration on a set privacy budget. But I'm not sure on the newer results. Maybe there might be better techniques. And actually, I think I remember that this paper, the first one, claims they have better results because of their greater number of iteration, but I don't remember on what benchmark. But they did some benchmarking on some DP. Um, so yeah, Rényi filtering is definitely useful when you are interested in accuracy and how efficient you want to be with your privacy budget. However, you still have to consider um, uh, um, other, let's say problems like what are you allowed to publish? Are you allowed to publish the loss of the function, or do you want to publish the loss of the function? In that scenario, Rényi filtering is not useful because you cannot do that. You have to consider something else. Or for example, you can think about nonlinear queries, as we did. You have to compute the sensitivity of that function, and then it's not clear that RDP would be better in that scenarios. And their analysis was only on linear queries. So yeah, if you're interested in getting the most iteration from uh, your privacy budget, let's say training a network, Rényi filtering would be definitely useful. What do you mean by the loss of the function, as in the privacy loss of each individual? Yeah. I mean, but even so, even if we, oh, where is so? Yeah, even if we, oh, and actually, yeah, if we go, so if we go, oh, okay, here. So yeah, if you look here, yeah, you cannot publish this parameter. So usually it's easier to say, yeah, this algorithm is, epsilon delta, and you specify the result. But here with the parameters, they actually use the gradient itself. So you you have to keep them secret, but you can only bound the final results by your budget.
But here I have a question. Sorry that I interrupted. Um, this feels like you could figure this stuff out. For example, if you have a point that has like a gradient norm that's huge. Oh, or the gradient norm here is it's limited, right? You have a finite norm on the gradient.
Well, in example with the gradient descent, yeah, you still clip it. Um,
Okay.
so you,
Otherwise, you could imagine a case in which you
yeah,
can actually
yeah,
distinguish quite easy.
yeah, okay, yeah. You can think that you can still limit them in the final scenario. Okay. Uh, well, if there are no more questions, I think yeah, that's pretty much all from me. But we can definitely continuities on Slack. So if there are more questions there, I can try to answer. Maybe also other people that are more experienced than me could jump in. So I have to admit I maybe don't have all the answers. But yeah, that was pretty lovely. And yeah, thank you for your attention.
Yeah, thanks a lot for presenting this
Oh,
this awesome work. Oh, there are some questions in the chat.
No, no, no.
Please unmute.
oh,
Don't mind. Don't mind.
okay, okay,
My bad.
okay.
Kwa, I think you raised your hand as well.
No, I was just trying to give a like a thumbs up or something.
Great. Yeah, it was a very interesting presentation, and it's I think it's one of the relaxation of DP that it's really interesting to study. Um, and thank you to you for presenting it. And if there are no more questions, then I will wait for uh, self nominations on the next uh, reading seminar for Open My Research uh, in my by Slack, right? Well, thank you everyone for joining, and see you next time. Bye bye.
Thank you. Bye.
Yeah. See you.